Okay, it's a great honor to be here. As Roland mentioned, I was attending my first Löwdin symposium, which I don't know if I just called it the wrong thing, in 2018. And so if you asked me then, would I be back here in 6 years? My answer would have been absolutely no. So I hope I'll do it justice, giving a little bit of a sense of where we started and what we were working on back in 2018 and how that's developed more recently. But first, I'm going to do a little bit of history, especially for those of you not familiar with my group. We were really interested in the world of open shell transition metal chemistry, and you've already heard a couple of talks today talking about that. So this may sound like old news, but we're interested in some of the challenges associated with open shell transition metal chemistry, particularly the diversity of ligand structure and size. Most of these are big molecules that are challenging to study with accurate quantum mechanical methods. These mid-row transition metals often have multiple accessible spin states, so we can have paired electrons at metal center, unpaired electrons, and the metals that I'm most interested in are these first row 3D transition metals that can in turn exist in multiple oxidation states. So oxidation states and spin states are a big challenge, which you haven't heard quite as much of. I started my independent career essentially in 2014. And one of the first things we did was we built a software suite called MolSimplify, where we're just interested in bringing to transition metal complexes what already existed in the solid state and organic chemistry community, which is making it possible to do high throughput data generation. And so what we did was simply automate the process of building transition metal complexes computationally. This naturally led us down the path of carrying out some of the very first machine learning model development for open shell transition metal chemistry, which I'll touch upon briefly today. Once you have representations, you can train a machine learning model. We also developed what we call uncertainty quantification metrics. So how do you know when to trust a machine learning model? When do you know its predictions are most confident? And in turn, when models are confident, we can do something called model exploitation, or when they lack confidence, we can do something called model exploration or active learning, which you've already heard about this morning, ultimately giving rise to design principles. So I'm going to tell you about a few applications of what we did, some success stories in this area, one quite recent, a couple quite a bit older, and then in the second half of my talk, I'm going to transition more to a second challenge we've encountered, which is if all what this is doing is accelerating density functional theory calculations, well, I just said that it's really hard to get accurate quantum chemical treatment of these spins and oxidation states. So how do we actually use machine learning, not just to get us to bad answers faster, but to actually start to overcome some of the limitations in electronic structure. So I'm being greedy, and I'd like to tell you both of those stories today. And so I'm going to go a little fast on both of them and just tell you what I think are the highlights in both of these areas. So to get something out of the way, because this will pop up and come in and out of my talk a lot of the time, we use graph-based representations of transition metal complexes. This is data efficient and doesn't require prior structural optimization of the structure in order to be able to make a prediction. It has many of the benefits of, say, using a graph neural network, but it's portable and can be used with kernel-based models, can be used with random forest models, and so on. And so we use this so much, I have to introduce it. These are called revised autocorrelation functions. We call them that because they're based on something introduced in the 80s called Murrow-Brodo autocorrelation functions. They're products and differences on the molecular graph of heuristic properties. This is what they look like. And the types of descriptors we tend to use, these atom-based descriptors that are just heuristics, we either sometimes refer to these top two, the nuclear charge and electronegativity. We call these electronic descriptors. descriptors. We call the bottom three covalent radius topology and identity geometric descriptors. That's just a rough classification of where they fall. And in using these descriptors, we were able to train machine learning models to predict things like the DFT calculated adiabatic high spin, low spin splitting. So normally this is a calculation that would involve geometry optimization of both a low spin and a high spin state. And so doing so would normally take hours to days, depending on the size of the complex. And now within a couple kilocal per mole, we can do this easily with our rack-based representation. And the only reason I'm telling you about this is because I'm going to keep referring to models we trained using racks, and so I have to show it to you once. But something that I'll actually come back to a little bit more is one of the things we like about choosing a representation and then using feature selection, as I've done here, to select the features that go into the model that are most informative rather than representation learning, is that it's very easy and quick to get feature importance. And so here are the rack features that matter for predicting the spin state of a transition metal complex. This pie chart on the left has a lot of blue, red, and green in it, which is telling you that what is going on at the metal center, as well as up to 2 bonds away, is really important for predicting the spin state of a transition metal complex according to the DFT functional that I use to obtain this pie chart. And I will come back to that in the second half of my talk. Whereas the redox potential has a much bigger gray wedge, and so the overall size and shape of a molecule determines the redox potential. And so we could very quickly see, more than just making rapid bad predictions necessarily, depending on how much we trust the DFT, we could very easily see that you can independently tune the spin state of a transition metal complex from its redox potential. And that if you wanted to design a transition metal complex to optimize its spin state, you would do something different than the redox potential. So we think this is cooler than just making predictions faster. But I will come back to that in the second half of my talk. So we had this machinery to be able to very rapidly assess transition metal complex properties after training on relatively modest data set sizes. And so we were interested in the model exploration example that I showed you on my first slide. And one of the first times we did this was in a paper that's now almost 5 years old. We were interested in just tackling multi-objective design challenges. And so one of the ones that we picked out was we first wanted to do catalysis, but then I thought, okay, let's pick something easier than catalysis. So we picked redox flow battery, redox couple design. I've since been told this is not in any way easier than catalysis, but I didn't know it at the time. So if you look into a redox flow battery, they're just very large off-grid storage of energy. They enable it by just sheer volume. And so what you want to be able to do to design a redox couple for this type of application is, for example, vanadium-ACAC complexes are one of the oldest known technologies where a transition metal complex works pretty well here. But the challenges that still need to be addressed are, first of all, can you make a molecule that's big enough that it will be stable and also resistant to crossover between the analyte and catholyte? That's something we addressed by how we built our discrete candidate pool. But then where we applied the multi-objective optimization was in addressing concentration. Specifically, we need a lot of this molecule to be soluble in the polar non-aqueous electrolyte, as well as maximizing the redox potential to maximize energy storage. So the way that we built up this candidate pool is we took 38 common heterocycles that are common in the Cambridge Structural Database. You've already been introduced to the CSD this morning. We fused them together to form 779 novel core ligands, added functional groups, added 4 mid-row transition metals, which are earth abundant but relatively underexplored for this type of technology. And the result was we easily created 2.8 million bulky transition metal complexes. Note that these are all homoleptic transition metal complexes, so they're maximally chemically diverse. You heard today how just mixing a dozen ligands can trivially lead to billions of complexes that ultimately don't have that much differentiation between them, but these are maximally diverse in the sense that they're all homoleptic compounds, and so they each have a unique ligand. And I'm going to show this as a cartoon first on this slide. I'll show the real data on the next slide. What we wanted to do was then take a method of uncertainty quantification and combine it with an optimization algorithm to then go out and explore and find the best compounds. And the way we're going to do this is something called 2D expected improvement with the the 2D expected improvement criterion within efficient global optimization. And so we'll write down our two objectives, log P for solubility and redox potential on the x-axis. And the first thing we'll do is we'll go to DFT. We'll spend a couple of weeks doing DFT, high throughput on GPUs. Then we'll train a neural net, and we'll ask the neural net, what do you think of these 2.8 million compounds? And what we're looking for is points that are going to go beyond this Pareto front. And we're going to score this with 2D expected improvement. The most promising and most uncertain points are the ones that our criterion are going to pick out. And the best candidates are then going to go back to DFT, and this is why this is an active learning workflow. We're going to reevaluate them and retrain the model. So I'll show you what this looks like in practice. So after about 2 weeks with DFT, this is all we got. These are big, bulky complexes, 100 to 200 atoms in size, each of these involving multiple geometry optimizations. But then in the matter of a few minutes, we can go back to the neural net. We can ask it, what do you think of this 2.8 million compound space? And we pick out the compounds that are most promising. You'll notice this frontier is lit up with high EI scores. And so we cluster and take some of the most promising compounds, and after another week with DFT, you can see the neural net was not that smart about the space. The Pareto front's only moving forward a little bit. But we retrain the model, go back to DFT again, and this time we've done a lot better. But you can see that the EI scores are going down, so the model is less and less optimistic that new points will be found. And so we do this again, and after only about 5 generations or 6 weeks on the DFT side and about 15 minutes with the neural net, we've really saturated our Pareto frontier of the best compounds that we can find with the neural net-based optimization of this 2.8 million compound space. And so we can take a look at which compounds show up on this frontier, what are the design principles we identify. And in particular, most of the points on this leg of the Pareto front, so they tend to have very high redox potential without sacrificing very much the solubility. Most of these are manganese high-spin complexes with oxygen coordinating atoms and sulfur in the ring, as well as small polar groups. And probably from that pie chart, if you thought about it, okay, redox potential depends strongly on size, you probably could have deduced that when we add the small functional groups, we need to keep them really small in order to keep the redox potential up. That's probably something I could have told you, but the sulfur in the ring and these other features are things that we wouldn't have necessarily known. For instance, this compound over here has bigger groups, which improves its solubility, but at the cost of hampering the redox potential. And so we were interested, you know, how much faster did we do than a traditional approach where we'd just randomly gone out and sought out compounds? So I asked my student at the time, you know, how much faster did we do? And he came back to me and he was very sheepish about it. He's like, listen, we only did about 500 times faster. And I was like, this is terrible. This is really not good. Because, like, you know, you get so used to people telling you all the time that they can do everything like 1,000 times faster, 10,000 times faster. But then you realize that the thing that we were doing 500 times faster was these DFT calculations that still took us 6 weeks running on about a quarter of my group's cluster, 64 GPUs already parallelized. So you take that and you multiply that by 500, and you realize that it would have taken us 5 decades to reach these same conclusions if we'd just gone out and randomly searched the space. So this turns out to be actually a substantial difference, a difference between having an answer in a month or two versus not having an answer in a lifetime. And so what I realized from that point on was that it's not so much how fast can we get to the result, it's how well can we pose the question. And I will not pretend that I'm the best at posing these types of questions. If anything, that's still an area where we need to improve. But that's where we started from that point forward, is thinking about, okay, what types of problems can we now start to solve? What are the multi-objective, multifaceted challenges we can address with machine learning, where searching large spaces and satisfying not just two, but more trade-offs can really help us to design materials in a new way. So this was work done shortly thereafter by Aditya Nandi, who graduated from my group in 2023, and will be starting his own independent career at UCLA in 2025. I think he's currently hiring grad students if anyone's looking for a position. So Aditya was working on a catalytic cycle that was of great interest to me and my group, which is the direct conversion of methane to methanol. It's an important challenge for gas to liquid technologies. And we've looked at this a few different ways, but specifically the multi-objective challenge he looked at was the fact that he was interested in simultaneously optimizing the hydrogen atom transfer, basically how fast will the catalyst be, as well as how quickly will it release methanol, because we need to release methanol to prevent its over-oxidation. And so here he created a 16 million catalyst search space, again a discrete space, where he created by taking heterocycles and fusing them together in rules that enforce symmetry to ensure that we created things that we already know about in the literature, such as porphyrins and corals, but also created whole new macrocycles. And so he ended up with, after functionalization with Hammett tuning type functional groups, he ended up with a space of 16 million catalysts. And so after, in total in the paper, we have about 7 generations of expected improvement. This is the same algorithm as before, but here I'm just showing the first 3 before the functional groups were added. The main observations we made were that manganese with oxygen coordinating the metal were actually really promising catalysts. And that having an anionic axial ligand would do a really good job of enhancing and preferring methanol release. And the anionic axial ligand is actually something that gets exploited in nature, so for smarter chemists we might have known that, but most of the community has focused on iron and nitrogen, so our screen revealed other spaces for people to look at in ligands that we could then propose, and we've talked to inorganic chemists about this. This is not necessarily that we want to tell them, please make this one molecule, but something that gives them a general design principle they can use. The other thing I'd like to point out is that this open shell transition catalyst space is a good example where scaling relations don't hold. So if there were a scaling relation between this release and hat, we'd see a straight line of some kind, but instead we see this type of scatter. So far I've told you 2 stories where we went out and we searched transition metal complex space. And when you think about all the transition metal complexes, you could think about the ones that have been studied experimentally that are in the CSD. You could think about the new types of hypothetical materials that I've proposed by, say, trying to obey reasonable chemical rules, but fusing together different rings and so on. And the challenge with these, the ones that I've proposed so far, is they may not be stable. They may not be synthesizable. So I'd like to propose new molecules, but I need someone to be able to make them. Now, a second challenge I won't actually cover in my talk today is the question of, if we think about everything that's been made experimentally, and we think about ones that we could hypothetically enumerate, well, still, do either of those cover the full diversity of the chemistry that's yet to be discovered? How do we actually discover new chemistry? And I'm going to sidestep both of those and tell you about a story where we think about this a different way. And specifically, there are many materials that have been made experimentally that have been made for one purpose. They were made because someone was excited about making that molecule, or they were made because they were useful in a specific application of catalysis. So someone out there already knows how to make them, but they may not have been studied for a particular use. And that makes life a lot easier for me as a computational chemist, because if I'm willing to do discovery in the space of things that have already been made, when I go to an experimentalist and I ask them, please make this one molecule, it will make everything better. I can at least hand them a paper and say, look, this is how these folks made it before. So I'm going to tell you about how we did that in our discovery loop. And before I get there, I have to give you a little bit of background. So I joined a center for polymer mechanochemistry in 2020, led by Steve Craig at Duke. And this was mostly a center focused on organic chemistry, and I love transition metal complexes. So I noticed that Steve Craig had also published this paper in Nature Chemistry, introducing one of the first to be studied transition metal containing mechanophore, specifically ferrocene. And he showed some interesting things here, but before I get to that, I would say I wrote to Steve and I was like, I noticed you wrote this paper on ferrocene mechanophores. Does this fit in the center? And he's like, well, not really. We're not doing this funded through the center. But I was stubborn. And we've done a bunch of organic chemistry with Steve and colleagues through the center. It's a wonderful center, but I really wanted to make ferrocene a part of the center, and now I'm pleased to say it is. So what Steve noticed is that when you incorporate these ferrocene molecules into a polymer, that there are two different mechanisms. There's either a low force mechanism or a high force mechanism by which the ferrocene breaks apart. If it's not covalently linked together, then it slips. It rotates and shears, and that requires more force to break ferrocene apart in a polymer. If you're not used to thinking about mechanophores, they're mechanically reactive units. You put them in a polymer and their bonds break first. But if you have a covalent lock between the two cyclopentadienyl rings of ferrocene, then you can actually break the ferrocene apart at a lower force. And so what you'd like to be able to do is put these into a polymer network, because it's recently been shown by the polymer community that if you have these weaker bonds in these mechanically reactive mechanophores, then you can actually create a macroscopically stronger material, because it's easier to break these bonds first and dissipate force. So we're interested in knowing, could we go out and explore the space of ferrocenes to be able to design ferrocene mechanophores without requiring this conformational lock? So could we do it through non-covalent interactions? And this was what I tasked my fantastic postdoc Ilya Kevlishvili with. I said, let's go out and explore ferrocene mechanophore space. And why that's compelling is that even though this was basically one of only two metallocene mechanophores that had ever been studied, there's about 5,000 iron-containing ferrocene derivatives with a single transition metal center in the CSD. So they've all been made, they've been crystallized, they've been characterized, and so on. So what I'm going to do is I'm going to attach polymer handles to them and actually start to simulate how they'll behave under force. And so from those 12,000 candidates, what Ilya first did was he simulated, using a method called COGEF, the reactivity of these ferrocene complexes under force for about 3% of the theoretical space that we could explore of 12,000. And indeed what he found was that if you compare the ones that don't have that covalent cross-linking to the ones that do break at lower force than the ones that don't. But there's this long tail here. And so we're going to call our cutoff for high force about 3,500 piconewtons. We're going to say that we have this sort of set of outlier points that look interesting that imply that we could break a non-covalently functionalized ferrocene at lower force than we would normally think for standard ferrocene. And so what Ilya did was he trained a multi-layer perceptron classifier using racks as the descriptors to predict, are we above that 3,500 piconewton threshold or are we below? And this did so with pretty good accuracy, ROC-AUC of 0.9. And so then he went back and he applied that classifier to the remaining 11,800 points we had yet to study. And we call this one-shot active learning because only after this one generation, we reached a very large number of compounds that were below that force threshold. And when we retrained the model and reapplied it to the new space, only very few compounds that had not yet been studied were predicted to have this low force. So what we did is we dug deeper into the points that were in this low force, highly reactive ferrocene space. And then we went exactly to the synthetic chemists and we asked them, can you make some of these for us? And we saw some really cool things. So we saw some ones that involved stacking, we saw ones that involved non-covalent interactions, and we saw ones that involved steric bulk. And this is where the compromises had to come into play. We had to propose just one to them to ask them to synthesize it. We couldn't ask them to synthesize every molecule lead we'd come up with. So we chose to focus on the application of steric bulk. And what I'm showing here is I'm showing the ferrocene control. That's the gray dashed line. Nuseg is the CSD ref code of the one that we picked out. It has both this trimethylphosphine on the cyclopentadienyl ring as well as this carbonyl. We kept at the request of the experimentalists, this was too synthetically complex to not just synthesize but incorporate into a polymer using ROMP. So we also looked at whether it would be feasible to just have the MTMS. And this is a control to show that if you moved it to an ortho position, it wouldn't have the desired substituent effect on the electronic structure. And in particular, what it's doing is the MTMS is stabilizing the transition state for the cleavage of the ferrocene. And as a result, it lowers the force. If you're not used to reading these plots, where these lines cross, this cutoff is where the molecule would break apart in single molecule force spectroscopy. So what we're predicting is adding this MTMS group will lower the force required to break apart this molecule. And so they made these molecules for us. They made specifically MTMS. And what they did is they incorporated them both into single strands, which they did sonication experiments that I'm not showing here, and they also incorporated them into polymer networks. And remember that if we put in weaker components, the polymer networks are overall going to be stronger, and that's in fact what they saw. So this is an experimental tear test compared to covalent control or just standard ferrocene. This is MTMS. You can strain MTMS about 4 times further. It has a 4-fold increase in network toughness in comparison to covalent control. And so this is something that we went from our molecular scale predictions of just our quantum chemistry and our small models all the way to a synthesized material. But what I think is really cool is that this is a phenomenon you can actually see with your eye. So these are the 3 materials. This is the covalent control, this is standard ferrocene, and this is the molecule that we designed in the polymer network. And all 3 are going to tear. The control tears first, ferrocene tears next, and our design polymer tears last. So this is the first time in my career, at least, that I've been able to go from a quantum chemical calculation to something that we can see with my own eye. So I thought this was awesome. But it's ultimately where I think we need to keep pushing ourselves. It's not just enough to design neat algorithms, but it's important to close the gap between computational prediction and experimental realization. And there are many ways to do that. So I'd like to finish. I've been going a little slow, but I'd like to switch gears now to a different topic that I will hopefully do justice in the next 14 or so minutes. And that's the other challenge that I think about a lot in open shell transition metal chemistry. And that's that, say I go to an experimentalist like I just showed you I did, and I say, please pick this one molecule, please make it, it will save the world, it will solve all of our problems. But I reached that conclusion using ML to accelerate DFT at one level of theory. And if I were to go back and do that again 5 years later with someone's better DFT functional, or maybe with a really fast linear scaling correlated electronic structure theory, that conclusion might be totally erroneous. And this has always been at the back of my mind. When we do machine learning accelerated DFT, we are inheriting potentially all of the challenges of DFT. So I was first interested in being able to answer how much bias is in an ML model trained on a single level of theory. Which single DFA should I use? If I can only choose one, how do I know which one to choose? Especially if I'm studying new systems where benchmarks don't exist. Is multi-reference character going to influence my predictions from, say, a single reference method? And how could I just avoid those difficult systems? Could I detect them and then avoid them entirely? So I'm probably not going to do all this justice, and I will just give you the highlights of how we've tried to start to answer some of these challenges using machine learning rather than simply blindly accelerating a single level of theory. So the first thing we did was we looked at data sets we'd been generating, such as 3,000 open shell transition metal complexes. Here I'm showing you the delta SEF computed homo-LUMO gap, which reduces some of the sensitivity of how homo-LUMO gaps are obtained because it avoids the piecewise linearity problem. And these are across all sorts of rungs of Jacob's ladder. And the interesting thing we first concluded was that even though functionals come from very different philosophies, there's actually a very strong amount of agreement. So I can pick here on the Minnesota functionals that tend to agree the least well. There's still a lot of structure in this data between M062X and BLIP. And then functionals you think come from very different philosophies have exceedingly good agreement. So the physicist meta GGA TPSS and chemist GGA BLIP. But this is really a function of which type of property we're looking at. If we want to get delta SCF gaps that are within 3 eV, that's roughly visible light absorption, then we can get different rungs of Jacob's ladder. We can get all the semi-locals together, all the hybrids and double hybrids together, and they'll all be fairly consistent on what it takes to get a delta SCF gap in this range. But if we ask the same thing of predicting a spin crossover compound, which I'm going to refer to as a transition metal complex with near degenerate high spin, low spin states within 5 kilocals per mole of each other. I'm happy to talk offline about further nuance beyond that. It's much harder to get different rungs of Jacob's ladder to agree. And we're curious why that was. And so this is showing latent space of the models I will show on the next slide. One of the things that was interesting is that DFT functionals tend to disagree more when there are mixing of strong and weak field ligands in the space, or when on average the ligand field strength is intermediate. So these circles are bigger when there's more standard deviation between the functionals. And that turns out to be exactly where you want to predict spin crossover phenomena. So it really depends on the type of property. How much bias are we inheriting when we use a single DFT functional really depends on the type of property we're trying to predict. So back to the pie charts I told you were my pride and joy from our early machine learning work. I was always really curious and kind of scared that our pie charts were an artifact of the DFT functional we used to generate them. And so this is one of the things we investigated. Here I'm showing the BLIP pie chart for adiabatic high spin, low spin splitting. It has the same features I showed you earlier, a lot of blue, red, and green in it, meaning that the spin is dictated by what's going on at the metal center. Here's delta SCF gap and vertical IP, which are very similar to redox potential, a lot more gray, indicating a lot more size dependence. And so we can pick on functionals that didn't agree that well with BLIP. That would be M06L and M062X. And you can see the pie charts are changing very little. They are different, but they are changing very little. And you can very clearly tell what's a spin pie chart from an IP or a gap pie chart. And the same holds true even if you go all the way through the effort of doing double hybrid calculations, which at least some people believe give rise to more accurate predictions of transition metal complexes. Other people obviously disagree, but we can all agree that they cost computationally more than doing the GGA calculation. So this gives us not just when we do this feature importance analysis, we can actually come up with design principles that are relatively insensitive to where the data came from. And so doing this feature selection gives us a path to design rules. And the same applies if you look at basis set dependence, which I don't have a time to talk about. But what we can do is we can come up with a pie chart at relatively low computational cost and then use it to guide which very high fidelity calculations, perhaps even beyond DFT, that we then go ahead and do, knowing that certain atom variations are going to alter the property maximally. So the other thing we can do is if we have 23 different DFT sources, we can train 23 different neural nets. And we can apply them to a new theoretical space of 187,000 compounds and ask, well, where do spin crossover compounds show up in this space, and how different are they if we require at least half of our DFT functional trained neural nets to agree in comparison to a single DFT functional. And so here I'm showing that latent space again, and this is where the consensus-based ML approach selects our spin crossover compounds. If we picked on a single functional like a ML model trained on B3-LIP, we pick out compounds over a much wider range of this space. But the third thing we can do is we can go ahead and we can mine the literature for mentions of spin crossover. And we can look at where those end up in our latent space. And they end up here. So it's not guaranteed beforehand that just requiring DFT functionals to agree will lead to better prediction of experimental properties, but heuristically, that's what we observe. And in general, we can see that, in particular, that our models where they predict compounds that aren't found experimentally, they tend to be cobalt nitrogen, which just aren't studied as much. So the other thing that we might wonder is, even if we could choose this ensemble of different DFT functionals, maybe there's still places we had no business running Kohn-Sham DFT because the systems are just too challenging. They just have too strong multi-reference character. And this always worried me too. Lots of these things kept me up at night. This was one of them. And so I like to think about multi-reference diagnostics as shining a black light on all of the data that we generated. So how much of it, where's the blood spatter? Where should we have never touched touched a DFT calculation? And you know, purists out there might say, well, everywhere. You know, you should never use DFT on a transition metal complex. But I had a feeling that there was a more balanced answer, and in fact, that's what we found. So we used, and I've cut most of the multi-reference discussion from this talk, which is already too long, but I'm almost there. But so I won't tell you about too many other diagnostics we've looked at. We spent a lot of time looking at diagnostics. This is this is originally work done by Eduard Matito and then reinterpreted by Jan Martin in terms of this R&D descriptor. Basically, some of the compounds we study have low multi-reference character, some have high multi-reference character. This was work done by Dr. Feng Liu, who's now a professor at Emory, almost up for tenure actually. And what she coined was that we actually had regions of low multi-reference character next to regions of high multi-reference character. And you could think of this as safe islands for simple electronic structure theories. That there are difficult compounds, but there are also lots of simple compounds out there. And we wanted to incorporate this type of awareness we were building into an active learning workflow. And so what we wanted to do was we wanted to design light harvesting chromophores by optimizing the HOMO-LUMO gap and minimizing the DFT-derived uncertainty from that. So we wanted to incorporate what Fong observed about multi-reference character, and we wanted to simultaneously optimize for small gap complexes, and normally you think the smaller the gap, the higher the multi-reference character, small multi-reference character, and we wanted all the DFT functionals to agree about the ground state of these open shell transition metal complexes, as well as the predicted property. And here we had a space of 32 million transition metal complexes, all with D6, cobalt, or iron. And what we were able to do was we were able to simultaneously optimize for the small gap as well as low multi-reference character. And we have an estimated 1,000-fold speed up of these what we call method-insensitive chromophores. So ones where we can robustly make the prediction regardless of DFT functional. And indeed, when we looked at where these ligands came from, they'd been used for other photochemical applications before, but just never in combination with these metals or other ligands. So now I have a couple minutes left for my last story. And I have 4 according to my little thing here. And so I wanted to, it needs more than 4 minutes, but I'm going to do it in 4. And that's the fact that there tends not to be a single universal functional for a given property of interest. And this is true for many things. It's especially true for predicting the spin state of a transition metal complex. And so we're interested in knowing if you pick a reference, and in the interest of time, my reference is DLP-NO couple cluster. Feel free to come at me in the question about that. We wanted to know, could you pick a DFT functional that reproduces an accurate reference? And across a set of around 450 complexes, our answer was no. So the best we ever did was about 6 kilocalories per mole. The worst we ever did was about 35 kilocalories per mole. The best is, in fact, a double hybrid. So this allowed us to move on to a different question of, could we have an oracle that predicts which is the best functional to use for each transition metal complex? And we'd like to get into this 1 to 3 kilocalories per mole accuracy range. And basically the answer is if we knew of the 48 functionals we're choosing from, which are the 10 best, which are the 10 that are the best, or even the best 5, or the best 3, then we would be able, if we picked and chose our functional, we would be able to predict something to within 1 kilocal per mole. And that's what we set out to do. So we use density fitting and take the atom-wise coefficients and pass them as inputs to a Baylor-Parnell style neural network. And then what the recommender does is it identifies the density functional with the lowest predicted error with respect to coupled cluster. And then we actually carry out that DFT functional. And the reason we do this is because doing the DFA recommender beats the best transfer learning models, so it achieves an accuracy of around 2 kilocalories per mole. I'm going to skip over the mention of whether or not this model performs better with lower multi-reference compounds, but here's an example of what it's doing well. If we took the global best double hybrid, we'd have an error of 9 kilocalories per mole on this particular complex, but our recommender instead selects omega B97X, which has an error of 0.1 kilocalories per mole. Because it's learning on the density, this is a very transferable representation, and so it does a really good job of identifying which functionals are best to pick in different regions of chemical space. And notice that no single functional is in the top 5 more than half the time. So really the right solution is really dependent on the chemistry. And we also need to test if the recommender actually works in a transferable fashion. So we looked at totally new ligands with different densitities and different chemistry than were in our original set. The model obviously gets worse, but it still does better than the underlying transfer learning models. And most importantly, we can see that the new best functionals are different than they were over the training and test set. And the recommender, because it's learning on the electron density, it adjusts its focus and it adjusts which functionals it selects as the most important. So I'm going to skip over why it works, just to say that Aaron Garrison has been extending this to a regression-based model, so basically a density functional that picks its own parameters now with some good success. And we can, for instance, pick the amount of Hartree-Fock exchange to include in a functional using the electron density, which is achieving about a 3 to 4 kilocal per mole error in the energy prediction that we want to achieve. So I'm exactly out of time according to my timer. I sped through that end pretty quickly, just to say that I've hopefully told you a story in 2 parts about accelerated discovery, but also peeking under the hood at the electronic structure methods that we use to accelerate all of our machine learning. And I'd like to finish by acknowledging the students and postdocs who did the work. And thanks for your attention.
Excellent. Thank you. Questions from the audience, please? I'll check this side. Roland?
Nice development since 2018. So if you in one sentence could say what's the major developments during the last 6 years, and in the next sentence say what's the challenge to address in the next 6 years, please.
One sentence for each, oh no. The biggest accomplishments in the past 6 years have been demonstrations of what you can do with very large data sets, which in my run-on sense includes language models as well as generative models. The challenge is in many areas of quantum chemistry, we don't have large data sets of high fidelity.
Here, Clémence. Just this one.
It works. Thanks for the nice talk. In the uncertainty of the DFT functional, I was wondering, I noticed that sometimes you actually use scan3C, you know,
Oh, we use that in the mechanochemistry.
Yeah, that was in the mechanochemistry, but I was wondering why not, okay, BLEAP is kind of your lower bound of what you are testing. Why not including also even lower, you know, HF3C, PBH3C, which can be very valuable sometime for...
Yeah, so we've never thought about using that in the recommender because we're already paying the cost of doing a standard DFT calculation, but that would be an interesting thing to think about. We were gung-ho about semi-empirical calculations, and then everything fell apart and was miserable, and this was pre-GFN. And then we went back to it a couple times with GFN. We're still pretty miserable about that, but I agree the 3C methods, if they actually are lower cost, because we're using such small basis set that I'm not sure that they're actually lower cost, but they certainly, they could belong in the recommender. That's a good point.
Still time for questions? Can I try something simplistic? trying to derive a design principle. You mentioned in the pie charts different regions in the metal complex determining spin state versus redox potential.
Yeah.
Does that reflect spatial extents of orbitals that are involved in determining spin state and redox potential? Is it so simple?
So spin state is definitely derived by the metal and the closest ligand atoms in the way that you get any spatial extent further away. We have a couple examples, but they tend to not show up in our data set, are if non-covalent interactions constrain the metal ligand bond and induce rigidity, whereas redox potential, definitely the redox event can be across the whole molecule. So yeah, it is something that someone with decent chemistry education could probably have come up with, but it's nice that our models are at least as smart as an undergrad.
Cool. Yes, I agree with that. Thank you for that statement.